Hi, welcome to the first lecture for our Physics 1103 course. Our course uses Giancolli's physics textbook for college algebra-based physics, and this lecture is on section 1.8 or chapter 1, section 8, okay? And it covers dimensional analysis. So first of all, what is dimensional analysis? Well, a dimension has a specific meaning. It denotes what base units you should use for the quantity. So for example, if you talked about what are the dimensions of distance, well, that would be a length. And then the SI unit associated with that would be the meter. Now, if you're talking about another quantity like a speed, you might be used to citing a speed based on what you might read off your speedometer in your car, like miles per hour. Well, if you think about what that means, miles per hour, then you're taking a length, which is a mile, and you're dividing it by a time, which is an hour. So the dimensions of a speed are length divided by time. Now, we could also refer to those things in terms of their SI units. So for example, miles per hour isn't an SI unit. Those are English units. If we wanted to switch over to SI unit, instead of miles per hour, we would say meters per second, and that would be the SI unit for speed. Oftentimes, textbooks use a specific notation to indicate the dimensions of something. In particular, they like to use square brackets to alert you that they're talking about a dimension and not a variable, for example. So the square brackets are there to help guide your mind and eye. And then they use symbols like capital L for length, uppercase M for mass, and uppercase T for time. So a lot of textbooks do that. Of course, they use the slash to indicate that something's been divided, and then they use a dot sometimes or an X, small x, to indicate that units are being multiplied. Also, you can raise units to a power. For example, we'll talk about an acceleration. The SI unit of acceleration is meters per second squared. And of course, they use superscripts to indicate powers in that case. Now, sometimes I do my dimensional analysis with the SI units because on a lot of problems, for example, beyond this chapter, you'll have to write down the units of your number right next to the number. You'll have to write them down, and that'll be part of the answer. And so it's good practice to start getting used to the SI units as well. Now, why on earth would you want to do dimensional analysis? It seems like you're just adding work, right? Well, not quite. Dimensional analysis is a really good sanity check. So, for example, let's say that you're working a really hard physics problem and you want to know whether or not your answer is right. Well, one of the first things to check is the units, because for sure, if the units are wrong, your answer is going to be wrong too, okay? Never fails. So make sure that you check the units and do some dimensional analysis on those more difficult problems especially to make sure that the units and the dimensions match the answer that you're supposed to be getting. For example, if you're solving for a time, it wouldn't make much sense for that answer to have units of meters per second. So make sure that you check that. Now, how does one do dimensional analysis? Well, there's some rules. And we'll have homework and we'll have in-class problems where you get to practice this. Oh joy, right? Okay. So dimensions, let's take them right now, length, mass, and time, and then combinations. We'll be adding units on as you learn more physics. But let's treat them like we would treat any other algebraic quantity. So what can we do? Well, we can add things, subtract them, multiply, divide, raise to power, all kinds of things. So we're going to do those to our dimensions and our units as well. Now, it's really important to follow these rules. If you have an equation, then the left-hand side of the equation and the right-hand side of the equation have to have the same dimensions and units. That's very important. Now, when you're adding and subtracting quantities, the quantities that you add and subtract also must have the same units, okay? Now you might have a combination of variables, right? And then you're adding and subtracting the combination. We'll do an example problem later, for example, where we have AT cubed minus BT, right? And it's not each individual part of that. For example, the a doesn't have to have the same units, but the combination at cubed has to have the same units as bt, if that makes sense. If not, an example is worth a million words, so we'll do one of those towards the end of the lecture, and hopefully that'll cement this idea. But to make it a little bit more clear, it wouldn't make any sense to subtract a time from a speed, for example. So if I said, what's 30 meters per second minus 1 hour? You should rightfully look at me like I'm an idiot, okay? Because that's not a clear thing to say. You can't subtract a time from a speed. You just can't do it. All right. You can, however, multiply and divide dissimilar units. In fact, just in the phrase miles per hour, division is implied. Miles is a length, per means divide by, and then hour is a time. So clearly there you're taking a length and dividing by a time, right? So you can multiply and divide dissimilar units. And you just do that like you would any other algebraic equation. One more rule for you, and then I'll stop and move on to some example problems. If you have a trigonometric function, or you have a power, that bit has to be dimensionless. So for example, let's say you're taking something, the sign of something, and you're writing sine of kx, okay? X in this case, let's say that it takes the commonly held dimension of length for x, all right? So that means that kx there has to be dimensionless. Well, if x is a length, then that means that k has dimensions of 1 over length, so that when you multiply k times x, then the lengths cancel out, and you end up with something that's dimensionless, okay? So any power, argument of an exponent, trigonometric functions, these things have to have dimensionless quantities. Okay, so let's talk about what the dimensions and the SI units of some common things that we're going to be dealing with for examples in this chapter are, all right? So we're going to be talking about lengths or distances. Those have SI units of meters and dimensions of length. Areas have SI units of meters squared and dimensions of length squared. Volume, SI unit is meters cubed, and the dimension is length cubed. A speed, the SI unit is meters per second, and the dimension is length per time. Acceleration, SI unit, meters per second squared, dimension, length per time squared. Okay? So those are some common ones. Now, there is one real limitation on how good of a sanity check dimensional analysis is. It can tell you whether your units are right, sure, but it can't tell you whether or not your number is right, okay? So you can say, okay, well, I got an answer of 3 meters per second, and I know that the dimensions should be length per time, so that checks out on my units. Great. Fine. But it can't tell you whether the answer should be 3 or 6 meters per second. That's the limitation, okay? All right, let's do a simple example problem, okay? This is something that you might see, for example, in a chapter 2 equation that you end up with. So let's look at this equation. X is equal to 1/2 times AT squared, all right? Well, we'll go with the commonly held convention that X is a length, okay? Or a position. All right, so the SI units are going to be meters, and the dimension will be length for X. Now we have an equal sign there, so that means that X and 1/2 AT squared have to have the same units or dimensions overall, all right? So left-hand side is length, the right-hand side has to be length too. Let's check that. First of all, let's consider each of the factors in that equation on the right-hand side in turn. We start out with a 1/2. Well, that's just a number, and there's no units or dimensions associated with the quantity 1/2, okay? That's it. So 1/2, we can ignore that part for our dimensional analysis and focus on the AT squared part. A is an acceleration, And as previously discussed, the dimensions of an acceleration are length per time squared. So in the equation here on the slide, I've got length divided by time squared for my units there, for my dimensions there in the equation. Next, I multiply by lowercase t squared. Lowercase t is the commonly accepted variable that a lot of folks use for time, okay? So this is a time squared. So in my dimensional analysis equation right here, I've written that as an uppercase T and then squared it. Now, if we look here, we have length per time squared times time squared. So those times cancel out, okay? The t squared cancels out on the top and the bottom. And that just leaves us with length. So now we've done our check, our sanity check. Yes, the left-hand side and the right-hand side of that equation have the same dimensions, and those dimensions are length. So sanity check complete, good, dimensions check out, units check out. All right? Well, that one was pretty easy. Let's do one that's a little bit harder. Let's consider the example that I alluded to earlier. You have the speed of an object, and the speed of that object is given by this equation. V, for the speed, is equal to at cubed minus bt. Alright, we'll go here with a commonly held convention that t is a variable referring to time. But we don't know what a and b refer to here. Okay? No commonly held convention for that. So let's figure out what the dimensions in units of those constants a and b have to be via dimensional analysis. Alright, here we go. So our equation, v is equal to at cubed minus bt. What do we know about this? Well, we know that units on the left and the right hand side of an equation have to be the same. And we know that the units of quantities added and subtracted must be the same. So what does that tell us? That tells us that the quantities v, at cubed, and bt all have to have the same units. Now, what are those units? Well, the SI unit of a speed is meter per second, and the dimensions of the speed are length per time. So that means that v has to have units of meters per second, at cubed has to have units of meters per second, and bt have to have units of meters per second. They all have to have the same units and the same dimensions, okay? Alright, so knowing that, we can move forward treating these quantities like algebraic bits to do our dimensional analysis. So since they all have to be the same, we can take each one in turn. We know that bt has to have dimensions of length per time, okay? So t, lowercase t, has dimensions of time. So that means that b times time equals length per time. So what do we do when we want to solve an algebra equation for b? Well, we divide both sides by whatever's multiplying b. In this case, time. So that means that b is equal to length per time divided by time, which is length per time squared. Now the SI units there would be meters per second squared. So that means that the dimensions of b are length per time squared, and the SI units of b are meters per second squared. Next, let's look at at cubed. Let's figure out what the units have to be on that. Okay, so we know that at cubed, just like every other bit in that equation, has to have dimensions of length per time. We know that t cubed is time cubed, so that means that at cubed is a times time cubed. So now we can divide both sides of that out by time cubed and solve for the dimensions of a. And that gives us that a is equal to length per time to the fourth power. And if you put that in terms of the SI units, that would be meters per second to the fourth power. Okay? All right. That's a more complex example for you. We'll do some more examples in class. I hope you understood that. Remember that anytime I post these online lectures, you should feel free to pause me if you need a second to catch up, okay? And you can always rewind me. That's something that you can't do in class. So I'll see you later. I'd also like to mention that, of course, this text that we're using for this class is Giancolli's Physics, Principles with Application. It's published by Pearson, and this lecture is meant to accompany material from that text for my class, Physics 1103. See you next time.